This video is about semiconductor diodes. It corresponds to section 22.1 of the Applied Analog Electronics textbook. Now there's two things we want to do in this video. One is to show you the symbols we use for diodes and explain what they do. And the other thing is to explain a little bit about how they do what they do. Okay, so the symbol we use for a diode is a triangle with a vertical bar. Some people fill in the triangle solidly, but that's hard to draw. I just do a hollow one. What does the diode do? Well, it's a two-terminal device, two connections to it. And what it does is it conducts current in only one direction. We can have current flowing in that direction, but not in the other direction. And the way to remember which way it flows is to look at the triangle here. It points in the direction the current flows. And so diodes can be very useful for a number of different things, and we will be looking at some of them in this course. How does it work? Well, it's a semiconductor, which means usually these days silicon. And the silicon has extra impurities added, tiny amounts, very carefully controlled, of elements like phosphorus or boron. And what we've got actually is the silicon with two different types of impurities. So I'm going to draw that as two different colors here. And what we've got is silicon, as you may remember from a chemistry class, has got 4 valence electrons. If you put it with phosphorus, phosphorus has got 5 valence electrons. And when you put the thing in a crystalline structure, it shares 4 of these valence electrons with the silicon next to it, and makes a very nice, covalent bonds with the silicon. You get a good crystal structure. But there's one extra electron that is very easy to knock out of the atom and have it float around as a free electron. So you have a fixed positive charge, where the phosphorus is, and a freely mobile negative charge, the electron. That type of silicon is called N-doped, for negatively doped, and it's got a bunch of free electrons in it that can move around. Those are called charge carriers, negative charge carriers, because they're electrons. Now, if you take the same silicon with its 4 valence electrons, and you put a tiny amount of boron in, boron's only got 3 valence electrons. Well, again, it can make nice covalent bonds with silicon in the crystal, but to get them all forming properly, it has to borrow an electron from somewhere, one of the neighboring atoms. And indeed what happens is you get a fixed negative charge here where the boron is, and a positive charge that wanders around. The positive charge that wanders around is called a hole, and it's basically electrons jumping from one atom to a neighboring atom. So the hole is what you can think of as moving around. It's actually electrons moving, leaving a hole behind them. But it's easier to think in terms of the hole moving, and so that's what we do. And this sort of semiconductor is referred to as p-doped, because it has positive charge carriers, the holes. All right, so what happens if we have a bar of silicon, part of which is p-doped, part of which is n-doped? Well, in the region near the junction between these two regions, the holes and the electrons are attracted to each other. They're opposite charges after all. And the electrons fall into the holes and cancel them. It's now neutral there. There's no missing electron. There's no extra electron. And so you end up with a region in the center here called the depletion region, where there are no charge carriers. That means this doesn't conduct there. So you've got a conductive region on one side where there's extra positive carriers. We've got a conductive region on the other side where there's extra negative carriers, and a depletion region in the middle where there are no charge carriers. Basically, conductor, insulator, conductor. It's a capacitor. What happens if you put a voltage, the two ends of this thing? Well, it depends which way around the voltage is. If you put a positive one on this side and a negative one on this side, well, the positive is going to push the holes towards the other side, and a negative one on this side is going to push the electrons towards the other side, and that's going to shrink the depletion region. And if you get the voltage up high enough, you shrink that depletion region down to 0, and you get conduction. There's charge carriers crossing the depletion region, and you get current flowing through the diode. So if this side's positive on the left and this side on the right is negative, we get current flow. What happens if we hook it up the other way around and put the negative on this side and the positive on this side? Well, this positive charge is going to attract the electrons. The negative on this side is going to attract the holes, and you're basically going to make the depletion region thicker. It's not going to conduct. Capacitance is going to go down a little bit. Now, you can't suck a lot of electrons out of the semiconductor doing this, because remember, we've got a bunch of fixed charges here as well. They're not moving. They don't contribute to any current flow, but they do keep you from, keep the overall semiconductor being neutral thing. The thing does not have an inherent charge on it. So despite this notion of you got electrons on one side and holes on the other, that doesn't give you a net charge difference between the two, because there's also the fixed charges that we're not talking about. We're going to talk about the mobile charges. So conduction in one direction is easy. Conduction in the other direction basically doesn't happen, except in some rather specialized situations. We have some things we use this for. One thing is we've got something called a photodiode. And a photodiode, the symbol for it is an arrow, or sometimes a wavy line coming into the diode. That arrow or wavy line, or wavy arrow, I should say, really, it's got an arrowhead still, is representing light. And this is a photodiode. What's special about a photodiode? Well, if the photon gets absorbed by the silicon, or whatever the semiconductor material is, the photodiodes aren't always silicon, right in the depletion region, what happens, the photon gets absorbed there, and it causes an electron to get knocked out of the crystal structure. So you now have got a free electron and a hole. These free electron and a hole can be sucked up by the stuff on either side, giving you a current. That's called the photocurrent. And this photocurrent actually is in the opposite direction from the current that we would normally get. So if we can normally have current flowing from positive to negative, that direction, the photocurrent would be flowing in the opposite direction. And the photocurrent is very useful because we can use it to measure light. And that is, in fact, something that we will be doing in the lab that comes after this. We won't actually be using a photodiode, but a phototransistor, which is a little bit fancier. We'll get to that in a later video. Another thing we use diodes for, kind of the opposite of this, it's got the arrow coming out of the diode. The arrow still stands for light. What this is an LED, a light emitting diode. And the idea here is kind of the opposite of the photodiode. When the electrons cross the depletion region, as you get the charge going there, remember there was a hole and electron coming together there and annihilating each other. Doing so releases energy in the form of photons. And those photons, if you've arranged everything quite nicely, can come out of the entire diode as light. So light emitting diodes and photodiodes are both types of optoelectronics. And we'll be looking at both LEDs and photodiodes in the lab. I think that's probably enough right now for what semiconductor diodes are. I'm not going to go into a great deal of detail. If you really want to know more about how they work, you need to take a quantum mechanics class. And since that's not a prerequisite for this course, I'm just not going to go there.